Welcome back to the video series on integration and differential equations. Today we're going to talk about homogeneous differential equations with constant coefficients. Let's start off by talking about some notation. There are three common ways to write the second derivative of y with respect to x. We could write y double prime, or we could write d squared y by dx squared, or we could write capital D squared y. So we'll practice all three types of notation as we go through some examples. Here's our first example, and before we jump into the calculation, I want to talk about what type of DE this is. We call this a homogeneous DE with constant coefficients. So the homogeneous part refers to the fact that we've got a zero on the right-hand side. So let's contrast that with the idea of a non-homogeneous DE. A non-homogeneous DE would have a function of x or a constant over on the right side. So non-homogeneous if there's some function of x other than 0 on the right side. Homogeneous means you've just got a nice 0 on the right side. Okay, and then as well as being homogeneous, our DE has constant coefficients. So what that means, when you look at the left side and you look at the coefficients of the y double prime, the y prime, and the y, those are all just numbers. So our coefficients here, 1, -1, and -6. So homogeneous DE with constant coefficients. Let's talk about how to solve this sort of DE. We're going to set up what's called the auxiliary equation. And the way that's going to work, we're going to look at our DE and we're going to replace the y double prime with an m squared. Y prime will be replaced with m. Y will be replaced with 1. And if we had higher derivatives in here, we could figure this out in a similar way. So if we had, say, y triple prime, for example, in our DE, that would be replaced with an m cubed. So whatever the order of the derivative is, we're going to replace that derivative with the appropriate power of m. So let's look back at our DE and we'll create our auxiliary equation. Y double prime becomes m squared. We keep the coefficients in place, so we're going to go minus, y prime gets replaced with an m, and then for the y term again we're keeping the correct coefficient, so we're keeping the -6, and the y just becomes a 1. So we don't really need to write down that 1. We're just really saying that -6y term becomes a -6. Okay, and then we set that equal to 0. So that is our auxiliary equation. And in general, we're going to solve this equation either by factoring or by using the quadratic formula. So let's try to factor it. We'll see if we can come up with a couple numbers that multiply to -6 and add to -1. So if we choose -3 and +2, that will work, and we've got our equation here factored. We got our left side factored so we can solve the equation. Right, so the roots then of the auxiliary equation, +3 and -2. So now to come up with a solution to our DE, we just need to know what to do with these roots. If the auxiliary equation has distinct real roots, meaning real roots that are not repeated, we don't have any repeats when we list our roots, and let's call those roots m1, m2, etc., just so we can refer to them, then here's what the general solution to the DE will look like. We're going to have some exponential functions. The roots are going to go into the exponent. The roots will be actually the coefficient of the x in the exponent. And each term is going to have an unknown constant as a coefficient. So we'll have c1 e to the m1x plus c2 e to the m2x, and if we had more than 2 roots, then we would just continue to add terms in a similar way. So with that, we can write down our general solution for this problem. The specific roots that we found were +3 and -2. So our answer is going to look like y equals c1 e to the 3x plus c2 e to the -2x. And since we've just got two roots, we see that we have two terms in our general solution. So what this problem came down to was recognizing the type of problem. We said it was a homogeneous DE with constant coefficients. That tells us that we can set up and solve our auxiliary equation, and then from there we wrote down our general solution. So the only other comment I want to make about this is just what would have happened if we had seen different types of roots. Let's say, for example, we had repeated roots, or let's say we ran into roots that were complex numbers. So either of these cases we will handle in a later video. For now, we're just going to practice the situation of distinct real roots. Let's try a second example. So this time we're going to start with a DE, and we're going to have a couple of different initial conditions to go with it. Incidentally, if it's a second order DE, we're seeing that y double prime in there, then we're going to expect to have two different initial conditions. Alright, so in solving this DE, you might notice it's the exact same DE as we had in our first example. So I'm just going to write ... Imagine we went through our whole solution process here, and we came up with the following general solution. So y equals c1 e to the 3x plus c2 e to the -2x. So that is the general solution that we found in our first example. Alright, so now let's practice using these initial conditions. So first thing we know is that y of 0 is -1. So let's plug in x equals 0 and y equals -1. On the left side we've got -1. On the right side, when we plug 0 into the exponentials, each of those exponentials is just going to become 1. So we'd be getting c1 plus c2. Okay, now that doesn't immediately give us the value of either constant. So let's call that equation 1. We'll store that information away for a minute. Next initial condition involves y prime. So in order to use that, we would first need to calculate y prime. Alright, so looking back at y here, let's take the derivative. Y prime is going to be 3 times c1 e to the 3x minus 2 times c2 e to the -2x. Okay, so I'll put a box around that because that's a function, and we're going to be plugging in with that second initial condition. So we're told that when x is 0, y prime is 37. So plugging in, we get 37 equals 3c1 minus 2c2. And again, we've used the fact that when we plug 0 into the exponentials, we're getting 1. Okay, so let's call that equation 2. Now just for clarity, I'm going to recopy our two equations. Let's solve this system here by elimination. So let's say we want to eliminate C2. Okay, so easiest way to do that, I would take equation 1 here. Let's take equation 1 and multiply it by 2. So that way we're going to be creating 2C2, and then when we add these equations together, the C2s will be eliminated. So multiplying equation 1 by 2, we're getting -2 is equal to 2c1 plus 2c2. Okay, so that's our modified version of equation 1, and let's add these two equations together now. So adding, we're getting 35 is equal to 5c1, and the c2's are eliminated. All right, so now we've got an equation we can solve that tells us that 7 is equal to c1. I'm going to put a box around that. c1 is 7, and we can take that information, plug it back into either equation. So I would suggest, why don't we take that, plug it back into equation 1. So looking back at equation 1 over here, plugging in, we get -1 is equal to 7 plus c2. That tells us c2 is equal to -8. So now that we've figured out our two coefficients, we can go back to our general solution, which was back here. We'll plug in the appropriate coefficients. Y is equal to 7 e to the 3x minus 8 e to the -2x. So that is the particular solution that solves the DE and that also satisfies those two initial conditions in the problem.